It's our last lesson of Unit 3. There's only four lessons in this unit, but as you've probably noticed, they're all rather intense. Okay, they're all different types of infinite series. This last lesson talks about the Fourier series. So when we talked about the Maclaurin and the Taylor series, we talked about functions, sine and cosine, root of x, all those different functions, and we express them as polynomials. What Fourier series does is it's used for periodic functions, functions that continually repeat. And you see this everywhere. You see this from sound waves to oscillations to how alternating or AC current works. So it's a very widely used type of series because of the wide-ranging applications. So periodic functions, like sine and cosine, they repeat at regular intervals. In other words, let's look at these graphs here. The first one is just sine of x. The second one is cosine of x. Okay? You can see that sine of x is a wave. Okay? And every time it goes from 0 to 2 pi, or in other words, remember from radians, consider it as 1 revolution, this is known as the period. Okay? In other words, the function does something here. In other words, it rises, and then falls and starts to rise again. And then it repeats the exact same function. Okay, so it continues to repeat at the same period. In this case, the period is 2 pi. So every 2 pi radians, the sine function repeats. The same thing happens for the cosine function. It just starts at 1 rather than starting at 0 for the sine function. But every 2 pi radians, the function starts over. So that is known as the period. In other words, the way to write that is the function at x has to be equal to the function at x plus p, where p is the period. So looking at it on this graph, that means that if the period is 2 pi, then sine of 0 must be equal to sine of 0 plus that period, which is 2 pi. And that's equal to the sine of 2 pi. Okay? And we can look at this graph and see that that is true. So sine of 0 is 0. Sine of 2 pi is also 0. Okay? So that's what it's saying when you look at a periodic function. What the Fourier series is going to do is expand out functions in relation to sine and cosine, and we're going to get into how that affects it in a second. Okay, so we're going to start this lesson, and all of our periods will match what sine and cosine have, which is a period of 2 pi. Okay, we'll get into other examples later on. So before I show you the form of Fourier series, I want to explain exactly what it is. So Fourier series, they're an infinite series combining sine and cosine waves together. So what they do is as you combine different sine and cosine waves, you get much more complex wave functions. And I'm going to show you this by showing you an example. So this example that you see here is simply a cosine graph. Okay, you can see our function that's sitting down here. Okay, is the Fourier series for it, but with only the first cosine function in there. Okay, so not with the not adding additional terms later on. Remember how we had cosine x, then cosine 2x, 3x, 4x, and they continued all the way through. So this is an example where you don't have sine terms. You'll see when we start calculating out Fourier series that sometimes the sine terms cancel or the cosine terms could cancel as well. So what you're going to see is as this kind of continues on, the functions will build on each other. So in this case, we have a cosine function. Okay, so it starts, it's a wave, it continues. Then you'll see we'll add a cosine of 2x. all right, which changes things a little bit. Okay, so the cosine of 2x graph, changes, looks a little bit different. And as you look at these, as you add the functions together, you add the peaks together, okay? They might come to a point here. These low spots, okay, will essentially kind of stay the same. This piece where it's higher and then negative will actually subtract to some piece here. And you'll start to see that a new function, I'll swap to a different color, ends up being created by adding these two functions together. Okay, so you'll see that it starts, to increase. Okay, and the function starts to change. As we continue to add more and more and more of them, the function starts to take over a completely different form. So what I'm going to show you in this is actually a video that will play. So, as I play it, so this starts it, okay, and you can see that this is just a plain cosine function. Now, as I change n to 2, you see the function becomes more complicated. Okay, it adds a cosine function down here. Now, as I change this to higher, I accidentally went really high, to 9 or 11. The function gets more and more and more complex. This is actually a square wave. Okay, so what this square wave is actually showing is it's more or less an on-off. So on, off. This shows that for the most part, this is actually a function that jumps, and we'll talk about non-continuous functions later. But what combining these sine and cosine waves together allow us to do is create a function like that we otherwise, couldn't have created without using this series. Okay? Is now that you've seen it visualized, how do we represent these using a Fourier series? Well, like I said, we are combining sine and cosine functions together. So what we have here is just like in the Taylor series, we start with an initial constant that's not multiplied by any x function, and then we add a cosine of x and a sine of x with their appropriate constants. And you keep adding a cosine and a sine, but you add one within the function. So it becomes cosine of 2x and sine of 2x. The next would be cosine of 3x and sine of 3x. Okay, all the way to the end, again, for an infinite series, to a to the n, which is the constant behind it, cosine of nx plus b to the n sine of nx. All right, so you're continuing to add these groups of sine and cosine together. And just like when we've done Taylor and Maclaurin series, I'm not expecting you to keep, finding these terms and finding these terms. Okay, once we find the first few terms, you'll notice that it starts to stabilize. But unlike the Taylor and Maclaurin series, we don't use differentiation or derivatives to solve the constants. Instead, we integrate. Okay, so going to your items you remember from Unit 2. So there's 3 constants that we have to evaluate here. The first is our initial constant, which doesn't have a cosine or a sine behind it. And because we have a period of 2 pi, our integral is 1 divided by 2 pi times the integral of negative pi to pi. So if you add up those two variables, okay, or in other words, you go pi minus negative pi, right, because you're going from the top bound to the lower bound, you'd get 2 pi. So you're going through the overall period of 2 pi, and you're integrating the function you start with. The f of x could be x, root of x, or it could be a non-continuous function, which we're going to talk about later, okay? So if it's a non-continuous function, you might have 2 integrals because it might not have a value at x equals 0. An example of this would be 1 over x, okay? As you get to 0, it might not have a value, but as you get past 0, it does have one again, okay? Your next constants follow a similar pattern. They're, again, the integral from negative pi to pi. For the a constants, which are the ones behind the cosine function, it's the integral of the same function f at x times cosine nx dx, or cosine x, whatever the cosine is that's sitting here. Okay, x, 2x, or 3x, whatever it is for the constant you're trying to find. B of n is the same thing, but it's in the integral from negative pi to pi of f at x sine of nx dx. Okay, those are the three constant types that you'd have to remember. And again, I provide these formulas. I also will tell you which Taylor series I'm asking you to expand out, okay? So if I'm asking you for the Fourier series, you would use these formulas. The Taylor series, you would use the formulas that involve the x minus a. The Maclaurin series, you would use when it's at x equals 0. Okay, so I will tell you those things. Again, I don't expect you to memorize that. So let's look at our first example. Find the first three terms of the Fourier series for the function f at x equals 2x from negative pi to pi. So the first thing you'll notice here is the period, right, to the total kind of length of this function, okay, before it repeats, both before and after. So the period is equal to the first, the end, or pi, minus the beginning, which is negative pi. So this becomes pi plus pi, which is 2 pi. Okay, so that becomes important when we talk about periods that are other than pi, or 2 pi, sorry. So when we look at our formulas to use to solve for the terms, or the constants, well, these are all based on that period being 2 pi. Okay, so if you remember, our Fourier series is f at x is equal to a0, okay, which is the first constant, plus a1 cosine of x plus b1 sine of x. And this will continue going. So it becomes a to the n cosine of nx. Okay, so remember, we're going to have, this increases, so it becomes cosine of x and sine of x for the first terms, but then cosine of 2x, sine of 2x, cosine of 3x, sine of 3x, etc. So we have cosine nx plus bn sine nx. Okay, so we're going to focus on these first three terms just to look at doing each one of the integrals. Okay, so starting with a0, okay, that is equal to 1 over 2 pi times the integral from negative pi to pi of f at x dx. Okay, you're going to see in these examples they're pretty long in how long they take to complete, and that's because of the amount of integrals and the fact that each integral has bounds. Okay, so the fact that they have bounds also makes it longer. What you're also going to see is that there are several terms that will end up being 0. Okay, so if you really wanted a full Fourier series, you'd have to expand it out to more than the first three terms, but the method for each of them, for finding each term, is the same, okay, using these same three formulas. So for the first integral, f at x, in this case, is equal to 2x. All right, so if we substitute that in, we get 1 over 2 pi times the integral from negative pi to pi of 2x dx. Okay. I will leave in the 2x into there because I know that the integral of 2x is simply x squared. Normally I do take the constant out, but that's the reason I'm going to keep it in here. So the integral of 2x, like I said, is x squared. So we get 1 over 2 pi times x squared, and that's evaluated at pi and negative pi. So you'll see that the integral for the constant term is always going to be simpler because it doesn't have a cosine or sine x term attached to it. So if I substitute this in, all right, I get 1 over 2 pi times pi squared minus negative pi squared. Okay, sorry, negative pi squared. So negative pi squared is just pi squared. So what we're left with is 1 over 2 pi times pi squared minus pi squared, which is 0. Okay, so like I said, you will see a lot of 0 terms when you look at doing these Fourier series. The next term, all right, a1, is equal to 1 over pi times the integral, in this case again from negative pi to pi, of f at x, and in this case cosine of nx dx. Okay, and in this case n is equal to 1. It's our first term. Okay, so n matches, all right, the value within the subscript for each one of these terms. So if it was a2, it would be cosine of 2x, not 1x. So substituting these in, we get 1 over pi times the integral of 2x cosine of just 1x, so cosine of x dx. Okay. Now, if you remember back to our integrals unit, unit 2, if you have a function that's x and a cosine of x, you have to do integration by parts. So you're going to see that a lot of our integral pieces that we learned will come into play here. Most notably, you're going to have to do integration by parts a lot. And you're going to have to integrate a lot of sine and cosine terms. So knowing that, for example, the integral of cosine of x is sine of x, and the integral of sine of x is negative cosine x. Okay, so knowing those integrals, again, I know you have a formula sheet, but knowing those makes this will go a lot faster for you. So before I do this, okay, I forgot the bounds, so let's keep them here so we don't forget them. I'm going to move the constant outside of the integral. So we get 2 over pi times the integral of x cosine of x dx. Okay. In this case, for these types of integration by parts, the best solution is to pick u as the non-trigonometric function. So in this case, I'm going to let u equal x. So du by dx would simply be 1, or du is equal to dx. The dv term is equal to cosine of x dx. So remember, to find the v term, you have to integrate it. So v is equal to the integral of cosine of x dx. Remember, we just did that up here. So v would be equal to sine x. Okay, you'll see that I'll do that specific style of integral pretty quickly in our examples, and that's just remembering that this is the integral for it. Okay, similarly, if we have sine x, which will be the next constant term we calculate, you'll see I'll use this integral pretty quickly. Okay, so having these terms, we can now substitute them in. So we have that a1 is equal to 2 over pi, and this integral in brackets, remember, the integral of u dv is equal to u times v minus the integral of v du. Okay, so substituting that in, u times v is x sine of x, minus the integral of v times du, which is simply sine x dx. Okay, and remember, that's all going to be evaluated at pi and negative pi, both those terms, right? So I didn't write it in the bounds here, I just wrote it at the end to signify that both those terms have to be evaluated at that point. So if you do this, the integral of sine x, remember, is negative cosine of x. So we get 2 over pi times x sine of x. And since it's negative cosine of x, and we have a negative here behind the integral, this simply becomes plus cosine of x. Okay? And that's evaluated at pi and negative pi. The next item that it's very important for you to remember are the values of the sine and cosine function at these intervals. Okay, so pi, negative pi. You'll see some examples that might have, pi by 2. Okay, knowing what these are. So I'll do this kind of in a different color down here. You can also go back to our slide where I show you the graphs of just sine x and cosine of x. And when you're doing these terms, you can see the values for those items. So for instance, if we have, I'll draw two graphs here. Okay, and I'll draw kind of bounds here. So I'll have pi by 2 and pi. These would be negative. And pi by 2 and pi. Drawing the same here, negative pi and negative pi by 2. Pi by 2 and pi. Okay. So for cosine of x, okay, remember, I forgot to put some bounds here. The upper bound would be 1, the lower bound is negative 1 on the y-axis, and that's consistent whether, as long as the function is, cosine of x or sine of x, okay, without any of the amplitudes of the function changed. So for cosine of x, when it's 0 or at the y-axis, it's equal to 1. Okay, so starting at that point, then it goes down. Okay, it's 0 at pi by 2, and it's negative 1 at pi. And it's the same or a mirror, okay, 0 at negative pi by 2 and negative 1 at pi, okay? And that function would end up repeating, okay? So you'd see it go up like that. I'll erase that, but just to show you. So knowing those values is going to come in handy. For sine of x, okay, it starts at 0 instead of 1. Remember, the cosine function is actually out of phase with the sine function by pi by 2. I think we learned that when we talked about transcendental functions. So for sine, all right, the wave looks a little bit different. Okay, so we go up, all right, to 1 at pi by 2 and back down to 0 at pi. Okay, negative pi, we go the opposite direction. At negative pi by 2, it's equal to negative 1. And then it goes back up and it's equal to 0 at pi. Okay, and this would continue, okay, on that trend. All right, the waves are the same, they're just shifted, cosine shifted to the left, or you could say sine is shifted to the right by pi by 2. So keep those values in mind. So if I substitute, okay, a1 is 2 over pi, and if I start substituting in pi and negative pi for the bounds here, you're going to see why those graphs were important. So our first instance, we have pi times the sine of pi plus cosine of pi. Okay, so that was at pi. Then we're minus negative pi sine of pi plus cosine of negative pi. Okay, so a couple things that we know right off the bat. I'll do it in a different color here. Sine of pi and negative pi are both 0. Okay, so both these terms will cancel. Cosine of pi and negative pi, again, are both the same value. They're both negative 1. So this term would be negative 1, and this term would also be negative 1. So in this case, we get that a1 is equal to 2 over pi, and what we're left with is negative 1 in the first term minus negative 1 in the second term. So this becomes negative 1 plus 1, which is simply 0. So again, we get that a1 is also equal to 0. Okay? Again, we can expand them out further, and there may be a question that I provide you that I ask for the first 3 non-zero terms. And you'll see that certain terms in different functions, whether it's cosine or sine, will always be 0. So in a lot of instances, all the a terms might be 0 and the b terms are not, or all the b terms might be 0 and the a terms are not. Okay? So the last term we have to find, so we found out so far that a0 is 0 and a1 is equal to 0. Okay? So now we have to find b1. Okay? So b1 is equal to 1 over pi times the integral from negative pi to pi of f at x sine nx dx. Okay, remember it's our first term, so the value of sine is 1, or the value of n is 1, sorry, and f at x is equal to 2x. Okay, substituting these in, we get 1 over pi times the integral from negative pi to pi of 2x sine of x dx. Okay, once again, we're going to have to use integration by parts. We have an x and a sine x. We also have that constant 2, so I will move it out of the integral just like I did for the a1 term. So we get 2 over pi times the integral from negative pi to pi of x sine of x dx. Okay. Again, for this integration by parts, and you will be doing a lot of these style of integration by parts in Fourier series. So the method that I'm telling you kind of remains the same for all of them. The function you select for u should be the non-trigonometric function. So in this case, we'll let u equal to x. So again, du is dx here, just like it was in the first example. dv is the remaining terms, sine x dx. So v is, remember, the integral of it, and remember the integral of sine x is negative cosine of x. Okay? So with that, what we get here, if we substitute these values in, we get b1 is equal to 2 over pi, and remember with integration by parts, we have u times v, which is x times negative cosine of x, or negative x cosine of x. And this becomes minus the integral of negative cosine of x dx. So you can see the two negatives here become a positive. So I can rewrite this as plus the integral of cosine of x dx. Okay, just to save some space. Remember, this integral is all, or this integration by parts is all evaluated at pi and negative pi. Okay, because that is the period. The good reason to start with 2 pi is, remember, the sine and cosine tangent functions, they all have a standard period of 2 pi. Okay, so that's why we start in Fourier series with 2 pi, because the terms within the Fourier series are just multiple or infinite numbers of sine and cosine waves. So we know the integral of cosine of x is sine of x. Again, you'll be seeing these integrals a lot. So this is equal to 2 over pi, times negative x cosine of x plus sine of x. And that's evaluated at pi and negative pi. So substituting all of these values in, we get b1 is equal to 2 over pi times our first term, negative pi cosine of pi plus sine of pi, minus negative pi cosine of negative pi. Okay, a lot of negatives. Just make sure you keep track of them. Plus sine of negative pi. Okay, so we know that the sine of pi is 0 and the sine of negative pi is 0. Remember those graphs. The cosine of negative pi is -1, and the cosine of pi is -1. So in your first term, you have negative pi times -1, which is positive pi. Okay, so B1, sorry, wrong color. So you get 2 over pi times, the first instance is positive pi. And then in the next one, you actually have 4 negatives. So a negative times a negative is a positive, times a negative is a negative, times another negative is a positive. Okay, so 4 negatives here all come out to a positive. So you have pi plus pi, okay, which gives you 2 times 2 pi, or 4 pi divided by pi. And your answer after the end of all that is simply the number 4. Okay. So now we have the first 3 terms. You see the first 2 were 0, the third term was not. What you would see in this function is that the b terms would all be non-zero and the a terms would be 0. So if you continued this function all the way out, you would see that all of the remaining a functions would stay as 0. So now that we have the first 3 terms, we could write our Fourier series by substituting all the terms. 0 for a0. Actually, I'll write it out first for you. So remember, f of x was a0, okay, plus, in this case, we had a1, okay, so a1 cosine of x, and b1 sine of x, and that would continue on. A to the n cosine of nx plus b to the n sine of nx. So substituting our values in, here we have 0 for a0 and a1. So we're left with f of x is simply 4 sine of x. And that would continue on. Okay, so you could find, B or a2 and b2 as well. We won't do that. You saw how long this example was, finding the first 3 terms, but the format for it remains the same. Okay, so in here, and let's look at b1 as an example. Instead of sine x, you'd have sine of 2x. Okay, so you'd still do your integration by parts. Okay, nothing would change. This would become 2x sine of 2x, which would again become x sine of 2x. Okay, nothing would change except for the fact that you have a 2x now to do in your integration by parts. All right, same thing will go with the a term. So like I said, we saw functions that they may not be continuous. So our constant calculation, let's start with a0, was 1 over 2 pi times the integral from negative pi to pi of f of x dx, whatever that function is. If it's a non-continuous function, it means that it jumps, okay? So in other words, let's look at this function here. F of x is equal to 1, but that's only from negative pi to 0, okay? So you can see on the graph here, for a period of pi, from negative 3 pi to negative 2 pi, the value is always 1. It's a horizontal line. But the circle here is not filled in. And the reason it's not filled in there is because it's not valid when it's 0. It's less than 0, not less than or equal to. After 0, okay, so including 0 all the way up to pi, the function's equal to x. Okay, so that means the start of the function, okay, it has a less than or equals to, is filled in. The end of the function, pi, is not. Again, cycling back to here because the initial function of f of x equals 1 is valid for pi. Okay, so this is known as a non-continuous function because you can see that there's 2 separate functions being graphed here. F of x equals 1 and f of x equals x, where x will just end up showing a straight line moving towards the top right of our page. Okay, so with that, what happens is instead of having one integral from negative pi to pi, you have to break it up into two integrals. And each integral will represent one of these functions. Okay, so for instance, we'll go through an example on the next in the next page, but you have to break it up into two integrals. The first integral would be 1 over 2 pi, again if we're solving for the first constant, times the integral of negative pi to 0. So it matches the boundaries that I have listed here. And it'd be f at x dx. In this case, f at x is 1. Then you have to add the integral of the second piece, okay, because it's a non-continuous function. So the second piece is from 0 to pi, again, following these bounds, of f at x dx, the next function, which in this case would be x. All right, so it's a small item to change. The big difference is it doubles the work because you have two integrals to do. But other than that, all of the formulas you saw stay the same. Okay, so the big reason this changes is because you have to make sure you have the right boundaries in so you can evaluate your integrals. Example 2 is a non-continuous function. So find the first three terms of the Fourier series for the function f at x is equal to 1 for the interval of negative pi is less than or equal to x is less than 0. Okay, so the less than or equal are important, and I'll show you why in a second. And it's equal to x for 0 is again less than or equal to x and less than pi. So this is a non-continuous function, and what we see is at 0 and at pi or negative pi, the function will jump. In other words, it'll not have a value at one of the functions, but have a value at the other function. So at negative pi, f at x is 1, okay, but it's not valid for the second function. You can see that's what the less than or equals here versus the less than means. The same thing means that f at x is 1 is not valid when x is 0, but f at x equals x is the function to use when x is 0. And again, that's because of the less than or equal sign here. So I find it helpful for these. Looking at this, this looks like an intimidating function. But I find it easier when I just graph the function out. Okay, so if I start and I have, pi and negative pi, okay, I'll put 1 here and then I'll go all the way up to pi. I do 1 for obvious reasons because there's a 1 here. And the pi is because the second half of the function is x, so the largest value it would get to would be pi. So if we draw this, starting with the first piece, f at x is just 1. So that's just a horizontal line. It's valid from negative pi, and remember it's valid at negative pi, all the way to 0. Now when it gets to 0, it's no longer valid, so you have an open circle, okay, because it's not valid for that piece. At that point, the function becomes f at x equals x. So the first one, you'll have a solid circle here, and it's just equal to x. So it ends up being just a vertical line all the way until x is equal to pi. And at that point, again, you'll have an open circle. And what happens is it will continue. Okay, so now f at x equals 1. Okay, so that is a non-continuous function. So as you see here, that those jumps not only will they make for more interesting solutions because now we no longer have a function that mirrors itself, right? So the integrals are no longer from negative pi to pi, right? You'll see, and you saw on our last slide, it means we have two integrals, one for each function. But remember, if we go back to a sine function, okay, if I draw the sine function and I draw it, go backwards as well, we always had the same period. Okay, so we had from negative pi to pi. And you saw for these functions that the value at negative pi and at pi for sine x is both 0. Okay, it's the same value. And that caused a lot of these variables to become 0, and that's because a lot of terms canceled. When you have jumped or non-continuous functions that jump, you see less terms that end up equaling 0, and we'll kind of get into that when we do our example here. Okay. So this is a Fourier series. So what it means is we have f of x is equal to a0 plus a1 cosine of x plus b1 sine of x plus, and we keep going to our last term, a to the n cosine of nx plus b to the n sine of nx. Okay, again, we're only going to find the first three terms, but the method will be the same for all of the future terms. Starting with a0, remember, we have two separate integrals here because our function's non-continuous. So what we end up with is we have 1 over 2 pi, that doesn't change. Our first integral is the integral from negative pi to 0 of f of x dx. F of x for this interval is 1, so we're left with just 1 times dx, plus our second integral, which is 1 over 2 pi, times the integral from 0 to pi of our second half of the function, which is x dx. Okay? So doing these integrals, you'll see, for the constant term, it's always easier because it doesn't have the sine and cosine terms attached to it. So what we get is 1 over 2 pi. The integral of 1 dx is simply x, so this becomes x, evaluated at 0 and negative pi. And the second integral, using the power rule, we get 1 over 2 pi times 1/2 x squared. Okay, it's the integral of x dx. And this is evaluated at pi and 0. Okay, so remember, they're evaluated at different boundaries because the function's valid at different points. So substituting in these values, we get 1 over 2 pi times 0 squared, 0, not 0 squared, that's for the next one, minus negative pi. Okay, so that is for this first integral, plus 1 over 2 pi times 1/2 times 0 squared minus 1/2 times, pi squared, minus 1/2 times 0 squared. Okay? So if we simplify these, we get that a0. For the first term, we get 0 minus negative pi, which is pi. So we get pi divided by 2 pi. And for the second term, we get 1/2 pi squared. Okay? The second term is just 0. So what we end up with is pi squared divided by, we have a 2 and a 2, so that becomes 4 pi. So these pi's will cancel. One of the pi's in the numerator will cancel on the second term, so we're left with 1/2, that should say 4. We're left with 1/2 plus pi by 4. Okay? The reason that term was 4 was, remember, 2 times 2 here is 4 in the denominator. So you see we get more interesting terms already just looking at the constant, right? Our next term, a1, remember, we break this up into two integrals. We have 1 over pi times the integral from negative pi to 0 of the first f of x, which is 1, times cosine of x. I'll remove that bracket so it's not confusing. Cosine of x dx, plus the integral from 0 to pi of, in this case, f of x is x, so x cosine of x dx. So the first integral is simple. It's just the integral of cosine of x, which is sine of x. The second integral, once again, you see that we have to do integration by parts. Okay? So remember what I said when we're doing these types of integration by parts. The non-trigonometric function should always be set as u. Okay? It makes your integration by parts easier. So if I do that, I'll do it in purple on the side here. U is x. So du becomes dx once again. dv is cosine of x dx. So remember, the integral of cosine of x is sine of x. So v is equal to just sine of x. Okay? Substituting in each of these values, okay, we're going to start by doing the integral of the first term. So the integral of cosine of x is sine of x. So we get 1 over pi times the sine of x, and that's evaluated at 0 and negative pi. And we get plus the second half, okay, which is our integration by parts, which is u times v, or x sine of x, minus the integral of v times du, which is sine of x dx. Okay, and remember, this is evaluated at pi and 0. One item I also forgot is, before plugging in that integration by parts, remember, this was all multiplied by 1 over pi, just like the first term. Okay, so I wrote it in blue. Again, sorry I missed, forgot to multiply that piece in. So, first thing I want you to notice is the first term we have, 1 over pi times the sine of x. Remember, going back to our sine function here, at 0, okay, sine of x is 0, so that's the first bound. At negative pi, sine of x is also 0. Okay, so what that means is this would become 0 times 0 minus 0. So this function is actually 0. Now to test this, I recommend that you actually have your calculator in radians and you try that. Try sine of 0 and try sine of negative pi. Okay, you should see that both those values come to 0. All right, so the reason I like to try and eliminate those terms earlier is then we don't have them kind of dragging along through the rest of the process for this. So it makes it easier, less confusing for you to have less terms. Okay, so what we're left with is that a1 is equal to 1 over pi times x sine of x, and the integral here of sine x is negative cosine of x. So we have a negative before the integral and a negative after, so this would become plus cosine of x. And this is all evaluated at pi and 0. Okay? If I substitute those in, we get 1 over pi times pi sine of pi plus cosine of pi, okay, minus 0 sine of 0, which again is just 0, plus cosine of 0, okay? So our first term here, sine of pi, remember, is 0, so this will cancel. Cosine of pi, right, is negative 1. And cosine of 0 is 1. So what we are left with here is 1 over pi times negative 1 minus 1. So our answer for this is negative 2 over pi. Okay, you saw now both of our first two terms, unlike the first example, have been non-zero. Okay, so a0 was 1/2 plus pi by 4. a1 is negative 2 divided by pi. So our last constant to find, right, is b1. So we found a0 and a1, if you remember. a0 was equal to 1/2 plus pi by 4, and a1 is equal to negative 2 divided by pi. So our last term to find is b1. Okay, so just like the first two terms, remember we're going to have two integrals. So we have 1 over pi times the integral from negative pi to 0 of, this one is f at x sine of nx. Okay, so remember n is 1 in all of our examples here. And f at x is also 1 for the first integral. So we're left with 1 times sine of x. Okay, plus the second integral, which is 1 over pi times the integral from 0 to pi of f at x sine x again. And this time, f at x is x. So we get x sine of x dx. Okay, so you see that the first term, we're going to be able to quickly find the integral of sine x. The second term, we're going to have to use integration by parts once again. Okay, so if we do that, remember, we set u equal to x. It's always the non-trigonometric function. So du is simply dx again. dv in this case is sine x dx. Remember, the integral of sine x is negative cosine of x, which means that v is equal to negative cosine of x. Okay? So our next step, we can do a couple things. We can integrate this first term, and then we can substitute in our integration by parts terms. So we get that v1 is equal to, in this case, the integral of sine, remember, is negative cosine of x. So we get negative 1 over pi times cosine of x. Okay, I just moved the negative outside just to make it easier for the math. And that's evaluated at 0 and negative pi. And that's plus 1 over pi. I won't forget the 1 over pi term like I did for the A1. And that's multiplied by the integration by parts. So u times v, which is negative x cosine of x. We have minus the integral of v du, which is negative cosine of x dx. Okay. Before I go further with this, you see that there's two negatives here. So I'm going to switch this to a positive, and it just becomes the integral of cosine of x dx. Okay. Remember that this second integration by parts will all be evaluated at pi and 0. Okay. So if we continue with this, we get that b1 is equal to, in the first case, negative 1 over pi times cosine of 0 minus cosine of negative pi. So remember, cosine of 0 is 1. Cosine of negative pi is negative 1. Okay, we'll use those numbers in a second. Plus 1 over pi times negative x cosine of x plus the integral of cosine of x, which is sine of x. Okay, and that is evaluated at pi and 0. So what we have in the first term is 1 minus negative 1 is 1 plus 1. So we're left with negative 2 divided by pi. In the second term, we have plus 1 over pi times negative pi cosine of pi plus sine of pi. That's the first term. Minus negative 0 sine of 0. Sorry, cosine of 0. I wrote sine. Plus sine of 0. Okay. So 0 times anything is going to be 0, and sine of 0 is also 0. Okay, and our last piece, sine of pi, is 0. So we're left with just the negative pi cosine of pi. So cosine of pi is negative 1. Okay, so what we end up with here is b1 is equal to negative 2 over pi, and our second term is plus 1 over pi times, our last term is negative pi times negative 1. So we have 1 over pi times pi. So the pi's here will cancel, and we're left with the 1 minus the 2 over pi term. Okay, so you can see in this non-continuous function, it's a little bit more interesting because a lot of the constants are no longer 0. In this case, none of the constant terms were 0. So now we can write out our Fourier series. So we have f of x is equal to a0, which is 1/2 plus pi by 4, plus our second term. Okay, in this case, it's negative 2 over pi, so it becomes minus 2 over pi times cosine of x. Then we have plus our third term, which is 1 minus 2 over pi sine of x. Okay, and this will continue on. Okay, but we only found the first 3 terms. So you can see that in this lesson, I'm only going to do 3 examples. We have 1 left, but each example is very long. Okay, so I don't assign you as many practice problems for this section because I know how long each of these problems will take. You watch me do it in lesson, it takes anywhere from 10 or 15 minutes just to do 1 problem. So our last item that I want to talk about is when we have periods that are not simply 2 pi. Okay, when we have them with 2 pi or something multiplied by pi, it's always more convenient because we have, for the cosine and the sine functions, we always have a value that's in radians. Okay, whether it's 0 and pi or pi and negative pi, there are always values that we can evaluate in terms of radians. If we have something else, instead of having negative pi is less than x, which is less than pi, what if we had, negative 2 is less than x is less than 2, right? Those aren't necessarily ones you can directly translate into radians. So we rewrite these formulas, but really, we're not really doing a whole lot, okay? We're starting with our period, okay, is still p, but it's equal to 2 times some length L, okay? So we have 2L here. So our length for each one of them, L, is simply pi, or simply half of the period. So instead of having, remember we had the integral from negative pi to pi. So in this case, we have negative L to L. And instead of having 1 over 2 pi, we have 1 over 2L. So basically, everywhere that we had pi previously, we're substituting in L. Okay, so L is just simply that length. So looking here, as an example, our period would be equal to 2 minus negative 2, or 4. So our length, our L value, is half that. Okay, so L is 1/2 of the period, or simply 2. Okay, remember when we had our integral from negative pi to pi, our period was equal to pi minus negative pi, or 2 pi. But the actual length was actually just equal to pi. Okay, so it was 1/2 the period, or pi. So all we're basically doing here is substituting in L, meaning an arbitrary kind of length and time. The second piece that we do is, remember, this was cosine of nx. Now it becomes n times pi x divided by L. All that is we added the pi by L term, okay, to convert all of our arbitrary lengths into radians. That's all that piece is doing, is it's converting it to radians to make it easier so that when we do our cosine and our sine integrals, we're always going to have some value of pi. That, again, going back to our graph, makes it easier for us to know these values, okay? Because if it's not in radians and then we start talking about degrees, it gets more difficult to calculate these. Remember, these should always be in radians. So that is, again, our only major change. All right, example 3, okay, which is our last example for this lesson. Find the first 3 terms of the Fourier series expansion for the function f of x equals x plus 2, negative 1 is less than or equal to x is less than 1. Okay, so what you notice here is when you have the bounds of the function, and you see that it's not a pi or 0 or typical terms that correspond to sine and cosine in radians, you know that the period is in 2 pi. The other way you can check that is to calculate it. So the period is equal to the upper limit, which is 1, minus the lower bound, okay, so -1, which is 2. Okay, so it's 2. It's not 2 pi, okay, it just says 2. So you know that this is not a typical period, okay? Knowing that, we can still calculate it. Remember, there were only slight changes to the Fourier series expansion. We basically replaced each of the areas that had pi with L, okay, being that length. And in the cosine and sine functions for the constants, we added a pi divided by L term to make sure we converted that period to ensure it's in radians. All right? First item we need to calculate is the length. So length L is half of the period, or 1/2 times 2, which gives us 1. Okay? So unlike in the previous term, we don't know that it's negative pi to pi. So we'll start by writing the function. F at x is again equal to a0 equals plus a1 times cosine of x plus b1 sine of x, okay, plus, and it keeps going, a to the n cosine of nx plus b to the n sine of nx. So now starting with our constant a0, remember, it doesn't change, okay? The only thing that changes is that we substitute in L. So we have 1 over 2L, and it's the integral from negative L to L, so -1 to 1, of just f at x dx. Okay, so that piece didn't change. So it's x plus 2 dx. Okay, so our first term, 2L, is 2 times 1, okay, which is simply 1 over 2. So what we end up with here is 1 over 2 times this integral. So the integral of x, remember using the power rule, would give you 1/2 x squared. And the integral of 2 would give you 2x. So it's plus 2x. And that is evaluated at 1 and -1. If we do that, we get 1/2 times, our first function is 1/2 times 1 squared plus 2 times 1 minus 1/2 times -1 squared plus 2 times -1. Okay? So if we calculate those out, our first term becomes 1/2 times 1 squared is 1/2 plus 2, right? So if you add those up, you would get 5 over 2. So you get 1/2 times 5 over 2 minus our second piece, 1/2 times -1 squared is +1. So we get minus 1/2, and 2 times -1 is 2, minus 2. So if you simplify this even further, again, you could have used your calculator. I'm doing it all, just by hand. We get 5 over 2, and our second term is 1/2 minus 2, okay, which is -3 over 2. So we get minus 3 over 2, okay? So in this case, what that comes out to is minus -3 over 2. That's positive. So we end up getting 1/2 times 8 over 2, or 2. Okay? Again, you could have put that in your calculator as opposed to doing all the fractions, and just place that number, okay, after you did all the major steps before it. Well, that's our first term. It's simply 2. Our second term, a1, okay, in this case, is equal to the integral of 1 over L, which is 1 over 1 times the integral from negative 1 to 1 of f at x, which is x plus 2, times cosine of, remember, it's n pi x over L. So n is 1 times pi x divided by L, which is 1. Okay? Multiplying that out, you get simply 1 over 1 is 1, so we can ignore it. Get the integral from negative 1 to 1 of x plus 2 times the cosine of pi x dx. If, now, remember we have an x plus 2, so we can actually break this into two integrals. If we do that, we get the integral from negative 1 to 1 of x cosine of pi x plus the integral from negative 1 to 1 of 2 cosine pi x dx. Okay? Again, for the third time, you see that we have an x and a cosine term, or x and a trigonometric function. So you know that one of these you will have to do integration by parts. Okay? So to do that, again, we're going to take u is equal to x. So du is equal to dx. dv is the trigonometric function, cosine pi x dx. Now, the trick here is you see that it's not just cosine of x, it's cosine of pi x. So if you take the derivative or the integral of that, you have to account for that additional pi term. So what that means is the integral, just like we had in the power rule, would be 1 over pi times the sine of pi x. Okay? Remember, we don't have that when it's just sine x or cosine of x, okay, because there's nothing behind that term. But now that we have the pi, you remember, if you take the derivative, you have to also take the derivative of the term inside, which is pi x. So that derivative is where that pi comes from. Okay, so you'll see that that's consistent kind of throughout what I do these integrals. Okay, so with that, we have all those terms, and we can now substitute them in. So a1 is equal to our first term, x cosine of pi x. We can now remember, okay, we can substitute in u times v, which is x divided by the pi term, sine of pi x. And that's minus the integral of v times du, which is 1 over pi sine of pi x dx. Okay? So all of that is evaluated once again at 1 and negative 1. In our second term, we can take the integral of directly. Okay? So the second one, it's 2. Remember, we have to account for this pi. So just like we did in integration by parts, it becomes times 1 over pi sine of pi x. Okay, and that's evaluated at 1 and negative 1. So the integral was the same. The integral of cosine is sine. You just have to take into account that pi term. Right? So we're almost there. You can see, it gets a little bit longer when we now have a larger function, in this case a function with 2 terms. But, the math has still remained largely the same. So to finish this off, we get that a1 in the first term, we have 1 over pi sine of just pi, because we're substituting in 1. Actually, before I do that, we have to do that integral. So I'm sorry we didn't do that. So let's backtrack a second. We still have one integral left to do. Kind of jumped the gun there. So we have that a1 is equal to x over pi sine of pi x. And this integral, again, remember taking into account for the pi, we have the integral of sine is negative cosine. So we're having negative here, and we're going to have a negative for that. So that'll come out to a positive. So we have plus, remember we have the 1 over pi term, we have to add another 1 over pi to account for taking the integral once again, to account for that pi term. So we get 1 over pi times 1 over pi. You can rewrite that as 1 over pi squared times the cosine of pi x. Okay? Again, that's all evaluated at 1 and -1. And we have plus our second term was 2 over pi times, evaluating this, we get the sine of pi minus the sine of negative pi. Okay, so substituting in 1 and -1. The benefit is, remember, sine of pi and sine of negative pi were both 0. So this term will just entirely cancel. Okay, so what we have left is just to evaluate this final piece that's integration by parts. All right, we're slowly getting there. If we do that, we get our first will be x over pi, which is 1 over pi sine of just pi, because we substituted in 1, plus 1 over pi squared cosine of pi, minus the same thing. We get -1 over pi sine of negative pi, plus 1 over pi squared cosine of negative pi. Okay, so the sine of pi and the sine of negative pi terms will cancel. Cosine of pi, okay, is -1. Cosine of the negative pi, again, is -1. So I know I'm running out of room. I'll change to a different color so that you can see. So what you have is that's equal to our first term, -1 over pi squared, minus -1 over pi squared. So you get -1 over pi squared plus 1 over pi squared. So that's simply 0. Okay, I know it's frustrating. You do all that work only to find out that that value for A1 is 0. Okay. All right, so we've calculated the first two terms. A0 was equal to 2. A1 was equal to 0. Okay, so our last term is now to calculate our B1. So B1 is equal to, again, 1 over L, which is 1 divided by 1, times the integral from -L to L, or -1 to 1, of f of x, which in this case is x plus 2. And now we have the sine function instead. So we get sine of n, which is 1, pi x divided by L, which is 1. Okay? So this becomes the integral from -1 to 1, because the 1 divided by 1 term is just 1, of x plus 2 sine of pi x. Once again, you can split that into two integrals because you have an x plus 2 term. So what we end up with is the integral from -1 to 1 of x sine of pi x, plus the integral from -1 to 1 of 2 sine pi x. Okay. Once again, integration by parts. It's going to kind of keep creeping in to each one of these functions. So for the first one, we do integration by parts the way we've done it in the past. So u is equal to x, and du is dx. dv is the remaining function, sine of pi x dx. Now remember, we have the pi in here, so you're going to see that it follows the same integration format that we saw for the A1 term. So the integral of sine of a function is negative cosine. So v becomes, we have the negative cosine, but remember, we also have to account for this pi term. So what we end up with is -1 over pi cosine of pi x. Okay? Just remember, when you're doing the period not being 2 pi, you're always going to run into these 1 over pi terms. All right? So now we're going to do the same thing where we're going to substitute all of these values in. So for our first integral, okay, we have u times v, which is negative x over pi cosine of pi x, minus the integral of v times du, okay, which is negative 1 over pi cosine of pi x dx. You can see I have two negatives. I like to kind of consolidate that right at the start. So we can delete that negative there and change this to a positive. Again, that's all evaluated at 1 and negative 1. And we have plus our second function, okay, which we can find the integral of once again. So remember, we just did the integral of sine of pi x, and it was negative cosine. So in this case, we have a 2 here. So we end up with negative 2, again divided by pi, taking into account that pi within the sine function. And we get cosine of pi x. Right? So that's a bad x. And that also will be evaluated at 1 and negative 1. So if we do this, first in the integration by parts, okay, we're going to finalize that last integral. So we're left with b1 is equal to negative x over pi cosine of pi x. And the integral of cosine, remember, is sine. But once again, we have to take into account the pi again. So we get 1 over pi squared, because we have a second pi term, sine of pi x. Okay, all of this evaluated at 1 and negative 1, plus, okay, or I guess it's minus, because we have the 2 over pi. So we can do minus 2 over pi, and if we evaluate this at 1 and negative 1, we get cosine of pi minus cosine of negative pi. Okay, so simplifying this, our first term, we get negative 1 over pi cosine of pi plus 1 over pi squared sine of pi minus negative 1 over pi, okay, just substituting in our boundaries, cosine of negative pi plus 1 over pi squared sine of negative pi, okay? And then minus our last term. So our last term here, cosine of pi is negative 1. Cosine of negative pi is negative 1. Okay? So what you see here is we get negative 1 plus 1, which is 0. So this term will actually cancel out. So we have now just our remaining terms. So anything times sine of pi or negative pi, remember, is 0. So this term and this term will cancel. What we have left with is cosine of pi, okay, which is negative 1, and cosine of negative pi, which is negative 1. So we get into this, negative on negative 4 times again. You saw that in a past example. So if we simplify these, we get negative 1 times negative 1 is positive 1. So this just becomes 1 over pi. And for our second term, we get negative times a negative, which is a positive, times a negative is a negative, times one more negative, like it ever ends, is a positive. So we end up with plus another 1 over pi term. So we end up getting 2 over pi after all of this integral math. Okay? So substituting each of these values in, now we have a0 and a1. Remember, we're 2 and 0. And we have our b1 term, which is 2 over pi. So f of x now becomes a0, which is 2, plus a1, which is 0, cosine of x, plus b1, 2 over pi, sine of x. Okay? Or simplifying this with the zero term canceling, we get f of x is equal to 2 plus 2 over pi sine of x. Okay, continuing on. All right, so you probably watched this in steps because it was a very long video, but really we only covered 3 examples. So take your time going through these. You'll see that each piece of this series is all involves math that we've already completed, whether it's derivatives of sine and cosine functions, or integrals of those functions, or integrals of x or x squared, using the power rule, or using integration by parts. So take some time to try these examples. Make sure you bring your questions to the tutorials, and that's it for this unit. So this last lesson gives us some time before the test, so make sure you bring your questions to the tutorial so we can answer it before the Unit 3 test. Okay, thanks everybody.